Today we're going to be looking at simulating your design in SPICE. Now, of course, SPICE, I've been a long time advocate of SPICE. I remember my first experience with SPICE going down to the basement of the university library to the big VAX machine. They had this giant manual that had about a 2-inch chain. You had to go in there and hold it on. But so fortunately, things got a little better. I think that's what eventually led me to go. I worked for Microsim for a while, supporting PSpice for a while, so it's one of those, excuse me. So it's always been something I've been interested in for quite a while. I know we've had SPICE in Altium Designer for some time. It's just that it hasn't been a real emphasis on it. So I think now especially with AD20 coming out with the new SPICE engine that they're incorporating, they're actually using ngSpice. I'll talk a little bit about that. And there's a little bit more geared towards revamping up the SPICE and simulation in Altium. So a quick introduction to, for our agenda, quick introduction. So of course, why simulate? Of course, it allows you to do, some level testing. You have your filters. You have some active responses on your design, which is easier, especially when you're prototyping, to get a, do you want to trying to decide on different changes and what to implement. You can do it at the schematic level. It's a lot easier than doing it once you finally get the finished board, making changes, or at the board level. Although you can want to test on a proto board if you can, or you can get your preliminary values and things simulated at the schematic level. Also, now in Altium Designer, we support the latest SPICE 3.5 and XSpice. Now, with AD20 coming out, as I guess one of our main engineers had retired, so I think they were trying to decide what to do with SPICE. We have a whole new team that's been working on integrating. Of course, ngSpice is an open source SPICE platform, but that'll be implemented in AD20. And of course, for the last 2 months, I've been working to make sure that once it comes out the door, at least it's decent. I think so. We've got of course, there's no additional licenses required to use your SPICE simulation. It's automatically included. It's been part of Altium for a long time. It's just that when you are running it, you wouldn't. I'll talk a little bit about the availability of libraries and examples, because when you first open Altium Design, there's really nothing there to really even indicate that SPICE is there. There's been really low-level priorities, and now they're making more of an emphasis. So hopefully we'll see over the next year. I'm so happy to see everyone here, and just as your support for SPICE. How many here in the room are actively using simulations and for validation? Okay, so the majority. All right, so when you initial install, SPICE is disabled by default. So you have your, and I'll show you if you missed it, how you can enable it. So but during the installation, you go into Platform Extensions and you click on Mix Simulation. That'll install the basic simulation engine as well as your libraries associated with those. So we've got, but otherwise, it's really easy to miss. You can install it. You won't even get that installed. So in that case, after the installation, you run Altium Designer, you go into your Extension Update tab. You can then click on the Install tab and Configuration, and you can enable your mixed signal simulation from there. So of course, the available simulation types are the standard, standard SPICE 3. You have your operating point, AC analysis and DC sweeps, Monte Carlo, temperature sweeps. There's a worst case analysis, noise, pole zero, transfer function. So your standard analysis types within the tool. And so getting started in Altium Designer. So where do you start? How do you even get started making a SPICE project? Well, you just create a standard PCB project. And so you can use that in the wizard, create a project, you can add your schematics, and then you start placing your components and wiring them. The main criteria is that, of course, your components need simulation models, so they won't simulate, and I'll show you how to validate and find components that have models. And your design needs to have, we'll talk about simulation profiles in a little bit, but the simulation profile and the advanced settings has a SPICE reference net name. So you need to make sure that that if you're using just GND as a default for your ground port, you have a ground port in your design. Otherwise, you need to make sure that you have a ground that matches the SPICE reference that you have specified. But the default is just GND. As well as simulation sources. You need some sort of stimulus in your design. So there's a number of sources available. So just using a power port won't apply a voltage value. You need to assign a voltage source, and we'll look at how to get those configured. You can assign the value in the component itself, but that really comes from the model, and we'll see how the model parameter works in the component. Now there's a SPICE toolbar. Of course, if you're using 8018 above, they've hidden all the toolbars. And the toolbar is really, and I'll show you the simulation menu in a moment, but from the toolbar, there's a source section. You can place sources directly from the toolbar. And there's some pre-configured sources, like plus or minus 5 and 12 volts. And then you have they have a 1 milli. And I'll talk about, it's a mistake which I reported because even though you can see down here, it's a 1 big M, but of course SPICE is case insensitive, so big M, little m means the same as milli. So we've got I think I've got the auto timer going. So we've got the sources down there. You have a sine wave, pulse wave, and I'll show you how to get those set up as well. Now when you add a model to your component, typically you'll get something like a value that's here. That'll come up, and that comes from the model itself. And historically, you've always had, the only parameters that would pass to your PCB were the value parameter, or the comment parameter, and your designator. So before, you'd have to go in, and for your comment, you'd set that equal value. And it really came about because of this simulation. A lot of your resistors, capacitors would have that value parameter, which is used for the simulation itself. And that comes directly from the model component. The model itself. So inside the source, when you edit the source, I have I had been working in the last 2 months in 8020, and so some of the screenshots are from 20, so I kind of made a mistake. But so when you're editing the source, and of course in 8019 or you go into the 8018 or 19, go to the properties panel, and you click the pencil next to the source. So when you edit the source here, it opens up the simulation model parameters. And there's a little column here called component parameter. And if it's checked there, well, now let me see if I can turn that off real quick. I've got the timings. Okay, let me go back in. All right. Okay, so now the way that, since SPICE is a kind of multi-domain simulation engine, when you look at the simulation source, it's a little tricky. They've named the parameters per analysis type. You have your DC magnitude, AC sweeps will start with an AC, and then the rest are going to be time domain. So you've got your DC, you have your DC magnitude, AC, your AC magnitude, and your phase, and then the rest are to set up like sinusoidal or pulse sources. So, but since that same source drives all 3 domains, so that's why when you come in here, you see all these different parameters. So you might come in if you want to set up your source and just enable the component parameter column. You just enable the parameters you want to see at the component, then you can set those values. Now for setting the values, you've got, of course, as I mentioned, SPICE is not case sensitive. You want to make sure that there's no space between the value and the unit multiplier. So here's this little chart of the supported prefixes. So you can use M for milli MEG for meg to differentiate them, or you can use the scaling factor like 1E3. So down here, and anything after the unit multiplier, it just ignores it. So like down here at the bottom, there's I have 5 meg HZ, 5 megahertz. If it's all together, it ignores the HZ at the end. So it equates to either 5 meg or 5E6. So you could put in either of those terms and they'll work. Now the SPICE simulation menu is where once this is where you access your simulation profiles and you can run your simulation. So there's also some other functions that we'll talk about a little bit here, but the main one is the SPICE simulation profile. And in here, it's really, in the SPICE simulation profile is where you set up the analysis types to run. So of course, at your general setup at the top, you've got your data collection, your sheets to Netlist. You can simulate your current schematic. If you have multiple schematics, so you can simulate all your schematics together of your whole project. You've got your SimView set up when you launch your simulation. I'll look at that in a second. But down here, you've got your show active probes or active signals. So so in the available signals, and this is where it helps. Before they had probes, you'd put in a net label on the net that you're interested in, and then that would come up in the as an active signal, and then you would put it over here, and it automatically gets plotted when you run to your simulation. Now, they added active probes, and those the current status of the probe, they are just static. So you place your probes around, and then that allows you to drive the signals that you're going to be evaluating in your SPICE analysis display. So you can cycle when you click up here, you cycle between either active signals, active probes, or it'll show all active signals and all probes. And then for the SimView setup, you can specify, do you want it to keep the last setup? So if you've gone in there and you made some changes, do you want to keep that same last setup display? Or do you want to, show the active signals, show the active probes, or show both signals and probes? You can also use the simulation profile in and out job. So if you create multiple simulation profiles, you can run them. You can target a single sheet. And so over here I'm showing it. So when you go to Mix Sim, so you have project or specific sheets. And you can have multiple profiles that you've set up. And you can import from I'll show you the profile manager. You can import and export your profile. So it's, don't know if it's as helpful now, but you can run several different simulations directly from your out job to then look at the data. From the menu, there is a probe manager. Of course, you can place probes from either the toolbar or from the menu place probe. There's several types of probes. You have your voltage differential, current, and power. Of course, the voltage or voltage differential, you can place it on a wire at the end of a pin. Current probes have to be placed on the end of a pin, and power probes can be placed on a 2-pin device that calculates using just the current and voltage of that device. There's a probe manager because you can get a lot of probes around. So with the probe manager, it allows you to set which probes will be active with which analysis type. Because in the simulation profile, you can configure one or more analysis type. You have your AC or DC transient. And for each analysis type, it'll run. So you can specify which probes will apply to which analysis types. And we'll see how those are displayed, because when you run an analysis, each analysis type will also have its own complete set of data, and I'll show you how that's arranged once you get into the waveform viewer. There. And so there's this profile view. So the profile view, the profile view allows you to go, instead of the probes, you have your profile, so you can switch back and forth between I don't have a picture of it there, but you have this profile view. So you can, instead of controlling your probes for the simulation, and now you're controlling which probes are going to work between the different profiles you've created. Now for AC analysis, you can set up the complex function in the probe manager here. So you can set it up for dB or phase delay, Bode plot. And this comes in handy because currently when you run a simulation like a Monte Carlo and you have a number of waveforms displayed, you have to change each waveform one at a time in the waveform viewer. So you can't select them all and to say, I want these all to be dB. So you can come in, you can change the magnitude to dB here and the probe. Then when you run it, all of those displayed waveforms, especially when you're running like sweeps or Monte Carlo, where there's a lot of waveforms grouped together, then it'll get the right analysis type from the beginning. How do you run it? How do you run a simulation? Well, there's two ways. So you've got from the click the run in the toolbar, or you can click from the simulation menu and click run. Now, when you start your simulation, you always want to go in and take a look at the message panel. There could be different messages displayed, why your simulation didn't start. And sometimes they're clickable if you double click on it, but it'll take you to the netlist. So, we'll talk a little bit about the netlist and how you can understand, at least, so if you put in a typo or an extra space or something, it'll say there's an error on that line. It's not as descriptive, so trying to figure out what the exact error was can be a little, but it'll say, but it usually gives in the message a little bit of information why it failed on a specific point. So for viewing waveforms, it creates a separate document called it's an SDF file for a simulation data file, and it's a SimView. And so, as I mentioned before, so when you start a simulation, it'll create a plot, and we'll look at what plots are in just a second for each analysis type. And as the simulation is running, you can take a look at your waveforms during the simulation. Now, stopping a simulation, of course, if you're in 8018, they've hidden all the toolbars, so it's like you can't stop it. There's no way. No, just kidding. Now, there's a toolbar called SimView Standard, and when you enable that, there's a little blue square. If it's blue, the simulation is running, and sometimes you might have a simulation that's just going on too long that you want to stop it. So if it's grayed out, the simulation's stopped. But if it's blue, then just click it, and then that'll stop it. Or that's an indicator that it's running. Of course, you'll see down at the bottom, there's a little indicator that the simulation is running. Now, for each enabled analysis type in the waveform, it'll create its own separate chart, which are represented by tabs of data. So down at the bottom, where I have these little arrows pointing, each one of these represents its own chart, which is corresponds to a separate analysis. So I've got the operating point, an AC analysis, and a transient time, which is a time-based analysis. And clicking on each one will then show the corresponding data for that analysis run. So it'll have its own set of waveforms available to display. Now there's a chart and plot. Well, there's a sim data panel, which will have all of your collected waveforms. So when you double click on one of these, it'll add it to your chart in what is known as a plot. And the plot will have your X, Y axes, and you can have multiple plots per chart. And the default, there's limited number of plots you can display, but you can enable it to have more than the default. I think it's like 3 or 4, but so each. And you can select, and I'll show you these. So when you can select a plot, and then you can add waveforms to that specific plot. So you can just double click it. You can also, if you have waveforms that are different magnitudes or a lot of different scale, you can add a second y-axis to your plot. So this here will be the plot. We've got the y-axis and the x-axis. You can add a second axis. Now, when you add a waveform to the plot, it'll have a little arrow depending on which axis is created. And when you add your waveform, it'll add it to the corresponding axis. But you can see like this here, this VCC is on this plot here, which is from 1 to 7, and I've got the output here, which is scaled up to 20. So I can overlay them so that one is not reducing the other when down. Otherwise, it'd be way down the bottom. You couldn't kind of see how they correlate. So you have the multiple plots, or y-axis there. So you have multiple plots here. So each one will have its own time. You can't. They're all used the same. You can't scale them individually. It uses the same base. So that might be something an improvement down the road. But they'll each have their own y-axis and x-axis scale. So where do you find your tech docs? So when you go to our documentation site, there's nothing mentioned about SPICE. I know that's our documentation team has been working on it. Now with 8020 coming out, they have their work cut out for them because now with the new simulation engine. But our older website, Tech Docs, has all of it. even though it's geared for pre-18, 8017 and below, it's still, most of the documentation there is fairly accurate, and you can apply it to the latest simulator. So when you go to techdocs.altium.com, you'll see a mixed simulation up in the corner. Just click on it, and that'll take you to the mixed signal section. Now, navigating around there, there's a little chevron at the top. The little three bars has lots of different names for that bar, but I just call it the chevrons. And then that brings up a little navigation panel that lets you go through, and it shows there's a tutorial. But the tutorial requires one of the older libraries. I'll show you how to download some of the libraries. I think the NSC library, as well as linking models. Understanding the Netlist template, which is really important, because although everything is under the hood and transparent, but when you're trying to debug and figure out what's wrong with your configuration, you need to know a little bit about the template. As well as this section here for the simulation sources. When you click on that, when you install the mixed signal simulation, there's really 5 libraries. There's the miscellaneous devices, which is installed by default, and that has like some simulatable resistors and capacitors, inductors. It has basic model, simulation models. It's not all simulatable, so you can't use everything in there. And I'll show you how to check in just a moment, how to check if there's a model associated with a component or not. And so if you click on simulation sources, then it'll give a listing of the types of devices in that. And then clicking on a device, it brings up the associated parameters. So it gives you a little description. How do you configure that device, especially like on a B device, which is a controlled source. It's a little bit more complex. You put in an equation. You can reference other signals. So this goes in and gives a little bit of information of course, they'll give the template format, and sometimes they'll give a little wire example as well. Now, hopefully, we can get some examples in the tool. Currently you can download. There's a lot of good examples, but they're in our old. You have to download them from the older TechDocs section. So I put a link up here. And if you download all the examples in a single file, there's a subfolder in there called Circuit Sim. And so that has a number of working simulations. You can just open them up and run them right out of the box.
We'll have access to these slides.
Yes. Yep. So the slides will be available. Now, of course, I had 80/20. I've done everything in the last. I've been thinking, living, breathing, thinking 80/20 the last 2 months. So. But the way that Altium Designer, when you install, it goes into the public documents under users, public documents, then it'll be version specific. So if you're using 8018, it'll be /8018, and you can specify that once you do during the initial install, you choose the folder, and then it puts an associated version. And so in there, you'll have your library. It'll be under mixed simulation folder under library. And so you'll have your simulation, your transmission line. There's a ABM folder. So you get these extra folders in under this. So this will be like Altium's as 8018 or 8019. Now, when you are experimenting or making your own examples and other things, just a word of caution, don't put your examples in the version-specific folder, because when you uninstall Altium, it'll wipe that folder out, and you don't want to inadvertently lose your examples. This Altium folder is pretty safe. I just put a subfolder in there with all my things in it, projects, and the uninstall won't touch that one, but anything that has a version number on it, you have to be careful. So to install a library from the components panel, in pre-18, it was the libraries panel, but now they've got the components panel. You click the little chevron icon, and you choose File-Based Library Preferences, and then that allows you to browse out and add a library. You have to be careful of the type, and sometimes you're adding a subcircuit or a model file or others. There's one in there that says all model types, so you can look in there, and so if you're looking in your folder and it says, where's my library go? It's you just need to check the type, and then you'll probably just need to change the file type, and you'll find it. Now, to download libraries, because It's our old legacy library downloads. I'm not sure down the road how we're going to distribute. I know for a long, I think the initial, when we went to all our libraries at the Content Vault scenario, it didn't quite support Spice models, so we missed it. But then they added it after that point, but we still don't have models in our Content Vault. So hopefully that'll be the next step, is a way that you can use, an easier way to use components directly from us. Now we have our older library download. You can download individual libraries, or you can download all the libraries in a single file, and those are all older legacy libraries. But of course, those are about 10 years old now almost. And I was trying to figure out how to get a copy of a spreadsheet that has all of the components in there. And I was actually going to bring up let me just bring it up real quick. And I'll give you guys my email, and you can email me, and I'll give you a copy of that. I've got this over here. So in this list, it's kind of an ugly list, and let me just switch this back over to, maybe I'll just do duplicate on here so I can see what I'm doing. So in this list, there is a column called model file. Because in the older legacy libraries, there's thousands and thousands of components, but not everything has a model. So there's this column called model file. And so if you look in there, if it has what I've done is I've clicked the filter at the top and said hide all blanks. So this is just showing all of the components with models. There's a lot of them, and it'll show the last corresponding integrated library with that. And so you can either download the library itself, and it's divided. You have your passive ICs are here, and it's got the integrated library is listed here, and it'll show the model library. Now, our integrated libraries that has the schematic and the model and everything all packaged into one library. So when you get the integrated library, it'll have all of the components inside of there. If you wanted to break them out, you could extract the sources to get access to the actual libraries themselves. Let's back. Go back to display settings, and see if it pops back up. Go back to current. Okay. So you can download either individual libraries or the entire library. Now to see if there's an available simulation model for your components, you can run a search. So when you click on the chevron, just do a file search. There's a click on the advanced function, and you can put in has model, then open paren, the sim keyword is a simulation model, and then the comma, then the asterisk that follows that is any simulation model name. So if you're looking for a specific simulation model name, you could put the portion of that with an asterisk in there, and then the end is just true, saying that okay, if it has a model, it'll return true. You can search for available libraries. Now, available libraries will look at your configured libraries that you have added in your component configuration, or you can choose libraries on path, where you can choose a folder, search through your subfolders. It'll search through all of your libraries and pull them up in here. I like doing that, especially if you download the entire library. What you do is you can right-click on the returned component, and it'll have an option to install that library. Just install it. Or if you try to place that component and the library is not installed to your configured libraries, it'll say, oh, your library's not configured. Do you want to add it? So you can search through your configured libraries, or even libraries you don't have configured on your hard drive. So for the types of components, of course, in Spice, there's 3 types of components you'll run into. You have your built-in components, which you really don't need an external model. You just assign a value, and it uses the built-in model. Then you have your intrinsic files, the built-in is more capacitors, resistors, inductors. You just give it a value, and you're off and running. Intrinsic, you've got more of a diode that would be one, or a diode or a transistor, where you have an external model file that has a bunch of parameters based on the characteristics of that device. So like the diode will have an external model that you'd have to use, and then a subcircuit which has its own library, which can be a collection of the built-in and intrinsic components building up a larger device to simulate a specific behavior. And so the models associated with that are going to, and it's really important that the extensions that you use if you're creating your own models. So you've got for the, of course, built-in, there's no external model, you just give it a value. Now for the intrinsic models, it's MDL, and our system, we don't parse through all the components, we only look at the extension. And then based on the extension, we decide what type of library that is. So you want to make sure for your models that you use the .mdl, and for the subcircuit, it's .ckt. And of course, with the models, inside typically it'll be a .model command, and the subcircuit will start with a .sub-subckt and ends with a .ends. Now, there's an exception, of course, where if you have a subcircuit, like I'm showing here, now down in blue, we have a model, and now that model is local to the subcircuit. So it's inside the subcircuit, and so that's why it's in here. Otherwise, we won't parse through a library to figure out if there's individual models in there with the subcircuits. So we're just assuming that it's going to be subcircuits in the .ckt file. Now, the next second we're going to look at configuring a netlist generation. Of course, there's a few different pieces to that. You have your SPICE template, the preview, and especially if you're building your own components, you want to be familiar with the syntax. So when you're adding a SPICE model to a component, you go down to Add Simulation. You'll get this window up here, and you've got you choose the device type. So there's several different device types. You have your general, and each one of these main categories will have its own setting of sub-devices, or the model sub-kind. So when you're in general, you have capacitor and diode, inductors, resistor. Those are more semiconductor. Capacitor and resistor are more semiconductor, which allows you to specify length and width within that model definition. There's a special generic editor here, which I'll talk a little bit about in a moment. So when you choose a device type here, it automatically will set the device prefix, because SPICE is really driven based on the very first character of the netlist. So if it's a SPICE prefix, and it's a little tricky to see down at the bottom you have the Netlist Preview, but because it starts with @designator. But you don't have to have your designator starting with that device prefix. It'll automatically put it in front of the designator, which I'll show you in a moment. But so the device type is pretty much set, puts it in there, and then you have the rest of the syntax. The Netlist template, based on your device type, will automatically be kind of pre-configured, and then we'll talk about how it builds itself. Of course, the supported device types, we have most of all of the devices. Of course, with XSPICE, we use the A character. So of course, when you look at the netlist, the very first character, as I mentioned before, is what drives the device type. And they have this list sort of in our tech docs. I stole this right from the NG SPICE manual. I liked the layout, but it's all of the device types are there that we support. So from the Netlist template, now this is what gets passed directly to the simulation model. And so based on how this is set up in the template, you can have required values. If you don't set a value, it'll come back with an error. So it's important to understand the template, especially when you are constructing if you're modifying, customizing that. Now, of course, you have your common syntax of what you commonly see, typically %. Will be a pen, and I'll talk a little bit about some of the other ones here, where the at parameter, where an at symbol says it's a required parameter. So if you don't have it defined, it'll come back with an error, versus the ampersand, which is a kind of an optional value. If it's defined, it'll use it. If not, it doesn't care. So we've got of course, % is the pen ID, and then you can have some if if-then check. So you have the question mark on a parameter. Does that parameter exist? And if it does, then it'll do whatever's within the, so down here on the bottom, whatever's within the pair. You can have the pairs can be commas or forward slash, vertical bracket. So you could say if this parameter is defined, include in the net list whatever's within those two pairs. Otherwise, it'll ignore those out. It'll drop it out. And you'll see that a lot when you're looking at the simulation sources, especially since it's kind of a multi-domain source, which it has different parameters depending on what type of analysis you're running. So there's really two types of parameters when you're dealing with simulation. You have your parameters at the model level. So when you click on the parameters tab, you'll have different parameters associated with your device type that you've selected. And you have the component parameter. You can check those. Those will make them component parameters. There's a special, as I mentioned, generic editor. If you choose that, any component parameter that you defined, it shows up in the list here too. So I'll come back to that a little bit later. Now down here at the bottom, see before we were in the Netlist template, now if you move over, there's a Netlist Preview. You can see what the Netlist is going to look like. So especially when you're building your own components, you get a little preview to make sure that, especially when you're dealing with different checks and parameters, you want to make sure that it looks right. Of course, you can still have mistakes here that aren't caught until you get and run a physical simulation. So if it looks good here and you're building your device, you want to make sure you put it into schematic, run a simple test on it, make sure you don't get errors. And that most common mistake I see is a user, they'll grab a model, they'll put it in here, they'll put it in their big schematic and start simulating, and their design's not working. And they're trying to troubleshoot that, and they can't figure it out. It might just be from a simple mistake. So you want to make sure you just run some unit tests. You make sure that's working. You're getting the results that you want from a single component, and then you put them before you use it in a larger simulation environment. So of course, the last step when you're adding a simulation model is mapping the component. Now the built-in components and intrinsic, they have a predefined order of the ports. So you have so over here where I have indicated here is the port map. And the port map is the kind of the internal SPICE mapping. So like for the diode, you have the model pin where it's going to be the first one is the anode and the second is cathode. And so you'd click on each one of these and you'd set it to map. So if you, depending on which, see I don't have the pins displayed here. Typically you want to turn the pins on so when you map it, you get the mapping right because you don't want to accidentally flip the component around. And it does kind of an auto matching. If you've done PCB design too, it does that auto map. It does 1 to 1, 2 to 2, so forth. But it might not be the correct mapping. So you want to make sure you come in and you change the mapping on that. It's a little bit easier when you're dealing with the built-in or components because those are predefined. But once you get into a subcircuit, which are the order of the nodes is really user-defined. So if you download like a subcircuit, an op-amp model, or here it's this 555 timer, you have a subcircuit definition, the name, and then followed by all of the interface nodes to the device model. You want to make sure that, hopefully if the model's good, they'll have good comments in there which port is which. So you just look at the parameters in the model, and then it allows you to map up your pins up above. So, and as well, so you just click over here, and I'll show a little illustration of that when we get to the demo. So you map all of these up, and they might match, but they might not. So in this case, they map, but depending on the order that they put them in, then you might have to match things up. Now you can really think of in the order of the subcircuit. Each node, you can think of it as a kind of a position. You have first position, second position, and so forth. So here, I put a little comment down. An asterisk is in the model file is the comment. So I put an asterisk for the position 1 through 8. And in the subcircuit, we have the names, ground, trig, out, and reset. So now you can see up underneath the model pin, the first number that's listed is the position. You think of that as the position. Then in the parentheses is going to be the name. So you have the position. So when we look at ground, you can see that it's position 1. That's why it has a 1 in front of it. And then it has the name G and D. Of course, since those are user-defined, it can be in any order. I think it's National Semiconductor. They like to use 99 and a couple different things for their powers. And so you'll get familiar with if you're dealing with different models with the different manufacturers and around. So we're going to look at the demo. We're going to take a look at some things in the tool itself. Let's duplicate this here. Now currently we have a SPICE simulation training. It's geared in 8017. So it's now we have an old tutorial, and I had the link in here, which let me just click on it. I don't know if I've got Wi-Fi in here. Okay. Oh, if I put the tutorial right in here, I'll right click and go to the hyperlink and open that up. So it's this link. If you go to the older tech docs, it's a tutorial, Getting Started with PCB Design. So if you just search on Getting Started with PCB Design, and this is our old multi-vibrator schematic. This is from the initial sketch on a napkin to a PCB. Now, fortunately, the reason why I'm going back to the old tech docs, they have a new tutorial in Exploring Altium Designer from 8018 or 819, whichever version you're using, but it all uses the content vault, and there's no simulation models. So they build the same circuit, but you can't simulate it. Here, everything comes out of the miscellaneous devices with the exception of the connector. So if you wire everything up, then you'd be able to just throw a source on there and run it. So and you're also learning PCB design at the same time. So now, if you take the simulation training class, basically on the connector, once you place the connector, if you edit that over here in the properties panel, you just go down and so I've already added one, but you click on Add Simulation down at the bottom, and that'll bring up a simulation source. Now, to get access to a source, I'll click on the model kind and drop it down and click on the voltage source at the bottom. And see now depending, so if I click on DC source, that just has DC, AC, and phase. So it's really just a 2-domain device. It's a little bit easier, so you don't have to deal with a lot of different parameters. If you choose some of the other model kinds, like because they'll all have a DC and AC component, but when you get the sinusoidal or pulse, they also have the transient time domain components. You just get more parameters. So if I leave this on here, I can even turn these off here unless I want an AC component on there, and I'll leave that as 8 volts. Now, while I have this on the screen here, so for example, if we look at the Netlist template, you have the at designator, and we have the %1 and %2, followed by at value. I don't know if you guys can see that back there in the back, but this is at value, and then it has a pound sign. So the pound sign says, it's similar to the question mark test, but the pound sign says, if anything within the brackets, the parameters exist, then output the text and within the strings. Otherwise, ignore everything after that point. We don't care. So what happens here is, so it checks for this AC magnitude. It's got quotes around it because it has a space. It's using this AC magnitude value. If I leave that blank and click on the Netlist Preview, I just have, see it says V1 as node 1, node 2, and it has the value that I put in here. If I put in a value, let's say like 1, simply you have to step off of there, and then I'll click off of back to Netlist. There's no refresh button, so you have to click off and back and come back. See, so now it's added, since I put a value here, now it's added that AC1, but also since it had the at phase, so it's checking if phase didn't exist, so it's coming back and say, oh, you don't have phase created. Now, if you didn't catch it here, when you run the simulator come back and error at you saying, hey, you don't have your phase set. So it's just, it uses these parameters to drive the template the value. So once you have a source in there, then you can run the simulation. Except since this is more of a multi-vibrator thing, you usually when you turn power things on, you'll get the power applies. But in the simulation, it's really an ideal environment. So there is, from the simulation sources, there's an IC component So you can see, so we can set the initial value on one of these components to kind of, so it allows it to start simulating. So if I go to my components panel, over here I can grab the simulation, I think, oh, this is the wrong one. Oh, got the, see, I don't have my, let me grab my simulation sources. I'll just go to File-Based Library Preferences and click Install. You have to be careful about this library path. We don't want to change that because libraries get installed relative to that path. See, so here I'm in my, I'm using version 19 library. I'll go under Simulation, and then I'll grab these. Just grab all the libraries here and hit Open. See, now down here, see, it's only looking for integrated libraries. So if you're adding a circuit or a model file, if you click down in here, they have all installable libraries, which will then give you access. If your library is not on the list, just choose to all installable libraries, and then that'll then show all of the installable library types.
Is there any issues with using older libraries within a program, or do you have?
No, yeah, you can still use integrated libraries. I know with if you're using Nexus, which they wanted more of a control, like if you're in a big corporation, there's more control. Nexus has limited it, so there's a way to turn on the legacy libraries in Nexus, but otherwise with Altium Designer you can still use your integrated libraries. So from here, I'll just go to my simulation sources, and I have my IC that I can then place down in. Now there's also a node set. So if you guys are familiar with node set is kind of like a first guess. So sometimes, usually the hardest part in Spice is getting it to simulate without converging. So an IC says we're going to start at that value and use that value. But the node set, the NC, says, okay, well, you can put those around, and you can say, well, it should start around, it should be in this area to get things working. So it's more of a kind of initial sort of starting point versus the IC is more absolute. And the way that the IC will work when you run it, and of course that's going to be for transient analysis. We'll just go up here to my simulation profile. I've got the let me just take my toolbar off. If I close my toolbar, see when you first come up, there's no toolbars. You just have your simulate menu, so you can access everything from your simulation menu. I like the simulation profile. The simulation menu called Mix Sim, and I'll just tack it right onto the left of my projects. The reason why I like to do that is when you, if I collapse that, it just pushes it off all the way to the left, and then I have access to these. But otherwise, everything is still available from the simulate menu. And then we'll just go to Edit Simulation, Mix Sim Setup, and you have your profile here. Now for a transient analysis, which is time-based, now the way when you first start an analysis, the default is to start in steady state. So it's just like you turned on everything, and everything charges up, and it's no longer, just nothing is changing. Everything is at a steady state value. So now, so when you turn it on like in an oscillator, of course you won't see any oscillation because everything is charged. So in here we'll use our initial condition. I want to talk about this initial condition setting, and I'll come back to here in just a second. So initial condition will then say, let's take all. It's like it's saying, okay, turn power on at time 0 and start collecting data, so it doesn't get your steady state response in there. So if I have my IC is on here and I run that, so this will set first let me run it without it. I'll just turn this off, and if we turn off the initial conditions here, and just as a kind of illustration, see over here I have these two capacitors. They're not going anywhere, but I call them CPV and CNV, where I've set an IC value on these capacitors as well. This is an illustration. So now I've turned off my initial condition, and I'll run it. Now this circuit has just enough to get it to oscillate, but it's so I've got my out 1 is here and my out 2 is here. Let me just go ahead and now in your waveform viewer, if you are going to add a new plot to add extra waves, I could add my wave here, but I'll just hit a new plot. You can give it a name. I'll hit next, and there's some configurations. The only thing that you can't do is select a bunch of waves to add at one time. You have to add them one at a time. So sometimes So you can add them here. If I add them here, I have to click on a waveform, click create, go back and add it one at a time. So sometimes I'll go all the way through unless it's like one, and I'll just add them from the SimWave viewer. It's sometimes a little bit easier. So I should have added, I didn't add a probe on these guys, but here's CPV. So I have to click on create, and then I'll add my CP in. Oh, that's CPV. You can also type in here CP. Give a CP in, so you can see it. I'll just add this one, CPV. I'll hit next and finish. And you can see, so here it's at zero. It's at 0, because we're not applying any kind of connection to it. So it's just when Spice first does the initial steady state, it opens all capacitors and it shorts all inductors. So and that's how it calculates the steady state response. So we see that's 0, and we have the and these are still. There was enough variation in the circuit to get these to start oscillating, but sometimes there's not. So sometimes you have to set a value over here. And I was experimenting putting initial voltage on here. I don't have anything set there for now. And let's just go back in and turn on the use initial conditions here. And let me look at the. Right now it's showing active signals and probes. So I'd lose my last setting, so I'm going to change that to keep last setup. So then it should keep my my last simulation settings. Turn that one off. Okay, so now I've got the I've got it's added. Well, I kind of messed this one up here, but I've got the 7 volts or 7.3 volts on the capacitor, and now you can see it's starting to discharge on there. So it's putting an initial value just from the built-in resistance. Of course, if you put a resistor on there, you can set the discharge rate. However, now the one thing is when you're using I think on one of these, let me get rid of this initial condition on. I think this one had a. No, this one doesn't have an initial condition on it, because the main difference between like an IC device, an IC says I'm starting at this value regardless of that and use initial conditions. So once you put this IC on there, it'll use it regardless, versus the initial conditions on components are optional. So if you have initial condition on a component, if you use initial conditions, it'll use those initial conditions on those. But this IC will always be used regardless of that initial use initial conditions that are here. Now, as far as calculating the overall time, you've got of course, you have your start time and stop time. Data collection always starts at time 0, but if you're running like for Fourier calculations and you have some settling time, you can say start data collection at a particular period, number of periods in, so then that way where the data has settled out and you start collecting data. But otherwise, but the simulation always starts at time 0, but although you can set a time past 0 for the start point, that's really just when it starts collecting data. And then you have your stop point here. Now the transient step, of course, is the step between each calculation, and the way that Spice does it, it does a kind of more of a linear interpolation between each calculated point where, and it has to do those within, we'll look at the tolerances within the specific tolerance ranges. So sometimes you have your transient step time. The smaller the step, you get a more accurate results. And then you have your maximum step time. Sometimes if your circuit is kind of settled and it's not moving, it might delay. You might not have any calculations. So at a certain period of time, you can force a calculation based on this max step if there's no calculations being made. And there's this use transient defaults. Now what this does here, it kind of helps you figure out what to put up in the other parameters up above. So in this section here, so this takes a look at the longest period of if you have a cyclical source like a sinusoidal source or pulse source, looks at the longest period of that stimulus, and it uses that as the number of cycles. And then you can specify the number of points per cycle. So you still have to do a little math. So you figure out the number of like if you have a really fast source, you want to get more points in there. I know I was experimenting with at least half of the waveform, but usually if you have a 1K, putting at least a quarter of the waveform as the number of points. 1 over the waveform times at least a quarter of that number. So you have the number of points per cycle, and then if you click the button here, it'll then use those calculated values. It doesn't automatically populate up here. You have this little button here called Set Defaults. And so what that does, when you click it based on these values, it'll update you'll see these numbers change even though they're grayed out. So if I make this like default points per cycle, and I think in here, I don't even have a stimulus source, but if I put more, so I'll bump this up to 500, we'll see that the transit step time is still pretty small, 20 nano, and I change it, I bumped it up, now it's down to 2 nano. So since when you're adding more points, it's reducing the transient step time. So with more calculations, and that can give you smoother transitions. A lot of times when you're looking at sinusoidal source and you look at your waveform and it's really choppy and all sawtooth, coming in and adding more points can help. And of course, you can if you uncheck that here, you can set those up manually as well. Now for temperature sweeps, I had set this up with I had been messing with Altium Designer 20, and I realized that it's not even out yet. And so, on here, so with the temperature for the temperature sweep here, there's 2 types because you have to have a temperature coefficient that you set in the component. So I set this one up in the model itself, and then over here I set it up as parameters. So Spice3 can support either one. Now, of course, with for PSpice support, and kind of the history behind PSpice, when you see PSpice models out there, is that before Spice3, Microsim had PSpice, now it's owned by Cadence and OrCAD. The Spice had made modifications to the syntax because to handle certain things that were deficient in the Spice 2. And so they had their own sort of format. Then Spice 3 came out, and so then that's why you kind of have these sort of 2 formats. You have the PSpice format, which has their own customizations, and you have standard Spice 3. So in Altium, we've done our best to support the PSpice variations of the syntax. Although going into if you get 80/20 with ngSpice, the PSpice support is not as heavy as it was in Altium Designer, so some things might not work as good. But that's the next phase of the simulation in 80/20 with the ngSpice implementation will be PSpice model support. Because a lot of manufacturers out there, PSpice had a really good model generator, so they use their model generator, so that's why that's a common fact when you download from the model, the manufacturer, they'll have PSpice and they'll say Spice 3. So you want to grab the Spice 3 model. If you're downloading a encrypted model, you're pretty much out of luck because different companies have encrypted them, so we can't use them, other companies.
So like for each Spice model, you'll be able to support those then?
Right, yeah, because especially like with their MOSFETs, they have a whole scheme of their own customizations. So anything that's specific to them, or if they're using encryption, yeah, we won't be able to support those. So you want to look for the Spice 3. And then majority of the time, if there's a PSpice model, if it's not encrypted, you can download and you can use that.
And like capacitors, the model, there's no voltage variation, or do you support the process?
Now in the cab, because we had in the downloaded examples, there's a voltage multiplier. So this there's a temperature example, and if you go to download the circuit sim, there's a PSpice, and it does have the voltage modifier which Microsim and PSpice had added, but the new ngSpice doesn't. It only supports it doesn't have the voltage multiplier or the value on the capacitor. So that might be something that might add in. We have that in 8019, so we support the PSpice voltage. And if I look at this model here and edit that, oops. Not signal integrity. So I click on the model file. So this has the temperature coefficients. You have a TC1 and TC2. TC1 will be your linear temperature coefficient, and TC2 is your quadratic. And there's also a TCE, which is the exponential. And it's usually one or the other. If it detects a TCE, it'll use that. Otherwise, it'll use the TC1 and 2. See, so in this capacitor, see, it has VC1, so it has the voltage modifier on there. But and when you go to 8020, that's not supported right off the bat. So of course, you have your TC1, TC2 modifiers in there, and at the resistor value, then they don't have these by default. So if I look at are defined by default in our components. And now modifying, like let's say if I wanted to modify a component, because as I mentioned before, when you're adding a model, it automatically determines the device type and sets up your prefix. But what if I wanted to make changes down here at the, to that template? So what you have to do is first you choose your device type, like resistor or capacitor. You click OK to exit out. Then you edit the model again, and then you change it to generic editor. Because if you don't save it the first time, when you change to generic editor, you lose everything. Now, generic editor is a special editing where it allows you can modify your template now directly in here. You have to be careful. The older subcircuits used to always default to generic editor. And one side effect of generic editing is when you come into the parameters, you get all your parameters from your components listed as well as your model. So it can get a little ugly in here. But but you can set it up with, so if you wanted to make changes, see, so here's, it's checking for length and width in here, or if you assigned a temperature. But you can also assign your TC1 and TC2 directly in the netlist, itself, and pass it as a component parameter without using a model. And that's just part of the, see, so here in the netlist template, there's the TC1 value and TC2 value, and then there's, I think, there's also TCE, I believe they'll support in there as well. So then with a temperature, now when you come in here, now with some of these analyses, like if like temperature sweep or parameter sweep, you have to run it in conjunction with at least one other analysis type. So if I'm going to run a time-based analysis and I want to run a temperature sweep, I would enable both of those. So here I've got my temperature sweep. Here you can set a starting temperature and ending and how you want to step it. And then in the general setup, you'll have your signals that you're going to use. And then once you hit OK here and run that, and so what it'll do is it'll run. Now for temperature sweep, at the end of each one, it will have a little underscore for the temperature run. So then you can see how that's running. It'll have one without the temperature on there. And then it'll have the rest with the temperature 1, sweep, and 2, so you can see kind of the temperature effects on each of the runs. And same thing for parameter sweep. Let me just go back over here, and we've got. Before I jump to the parameter sweep, I just wanted to have the 555 timer one, and this is just one example of mapping a subcircuit to a. Now, of course, you think of this as a digital part, but this is really just made up of a subcircuit of different controlled sources and other types of components. So if we look at the simulation model, and this is one of the examples that you'll find in the downloadable circuit sim. It's the 555. There's an A-stable. I think there's 2 different versions of that. And we go and look at the model file, and that might be kind of small, but see they have initial mapping, so they've got they'll show how they are mapping with these. They have little dashes down here on how they're mapping that. And they have a collection of components, resistors, controlled sources, and everything to run that. And this is where they, a lot of times when you download a model from manufacturer, they might have some notes in there saying, this model was derived using this particular advanced parameter. Gmin is set at this value, or that. So you want to make sure you read through the comments in the model, because sometimes there's some specific tweaking you need to do to get it to work. Or like in this one, you have to put this IC on the trigger in order for it to run. That's why it has a little IC on there. And then when you run that, it'll run through the analysis. Right now, so it says it's compiling. But now I also have, it's kind of interesting now because in the parametric sweep, when we show that, I was doing some benchmarking between 80-19 and even an 80-20. I just didn't add any signals on here. Oh, here I've got trigger. Go right click and fit. Oh, I must have it's real small on that one. So you can right click and fit document. You can zoom if there's an area. I'm not sure why that's not displaying in here, but so you can run a simulation. And so I found with the parametric sweep, it was nearly maybe 6 times faster with the new ngSpice. So it's a pretty significant speed increase. Now, on some of these components are right from the special. If I go to the components panel, I have the special function. And now the special function library, these are all XSpice type devices. So it gives you, there's several different items here. Like there's these are frequency controlled sources. So there's frequency controlled sine, square wave, triangle wave. A lot of times you might not find the particular model that you are trying to simulate. So you might need to use one or more devices to kind of to get the waveform that you want. So one of them, you can use these special functions. There's also PSpice functions. Now PSpice, what they had done is they had modified the controlled voltage source and controlled current sources with an equation. So there's a lot of, and they call it analog behavioral modeling. So you can get a lot of different waveforms created using those. Now with Spice 3, they came out with the B device, and the B device is an equation that lets you write in pretty complex formats. But we have the PSpice functions are here. And when you go into so you have a bunch of these math functions are all based on XSpice. So you have a number of different math type equations you can create, as well as I think the special one. I think in here there's one with in the simulation sources you have the B. There's a B. The B device is an equation controlled source. So you have a current controlled source as well as a BV source, which is a voltage controlled source. You can grab nodes on your schematic and manipulate them, or you can write an equation for these. So if I was to place this down on here and edit that, it has you have to go in and edit the simulation model, click the pencil, and you'll see that in the parameters they'll have an equation. Some of them will have multiple inputs. They'll have and kind of describes the naming convention of them. They'll have 2 inputs or 3 where they have multiple equations that you can set. But so that allows you to create more complex waveforms. Now in here I just have on this VPWL. Now the piecewise linear source allows you to assign voltage or current time pairs. So if I look at this here, so there's a little table here with this is just a voltage source, so I have the different time and the voltage pairs. So at each time, and it's a little tricky because in order to set it up, you want to set, like this is at time 0, it is 0 volts. And then at time like 100, the first transition, you want to keep it at the same voltage level. So at 100 microseconds, it's still at 0. And then this is going to ramp up. So I actually have a point. Unless you make a really small time point, like this from this 1 microsecond, it's going from 0 to 4 points. And sometimes if you make the transition too steep between points, you can cause convergence failures in your circuit because it just can't calculate based the tolerances on it. So that could be, you have to be cautious of those. So you come out, you have a flat line, then you come out with the next time point. Now, I was looking at the roadmap. I don't know if I can really see it, because a long time I've been missing kind of a graphical way to set this up. So I know that that's something they're investigating for more of a graphical way, but otherwise you can put these all in. Now, there is a trick you can do here too for if you set this to a file, then you can point it to a text file that has your time voltage pairs. You just put a column in, you have your time and your voltage paired spacing. I might have an example of that, but right now this is just going to do a simple ramp up. And so V sign, and I don't have my N2. Let me add that over there. Oh, yeah. So see, I had to go in here because sometimes there are some different. Because right now, when I put 0 volts in there, that's why these are failing. But I wanted to show that, and I'll pop over here. So here I've got. See, it's zeroed out over here, and then when it starts, I just have it jump up, and then that's when these start pulsing. So you can, and also if I ramp it up, I was trying some different steps on there. You can change the frequency on there, but on these now to get an initial point on here, because that's where you can. So in the VPWL, if I edit that, it has this initial. Actually, I did put a DC magnitude on there, and it's just complaining. Let me just put it on. I'll just put 0.2 because it should have, so it popped this up here, and it's trying to. Oh, I guess it hit the maximum on there, so that's fine. But sometimes you get a message on there because when you put 0 in there, it's a special condition. So if you put a small initial starting voltage, that can let you get around that particular message. Projects. So the piecewise linear file, and then one of the examples. So here's where you can set your simulation out to a file. So if you have a file that has just time voltage points, let's see what. Oh, so it's over here. It's so this is just it's time space voltage. So it's 0, 0, 0.1, 0.1. So it's just a roll. So you can have a whole list. So if you export that out, you can from Excel. You can use that file to then drive and stimulate your circuit directly from that file. So you have these are just being driven from the file, and when I run that, see, so it's generating this. Let me just change my settings here. If I go to Tools, Document Options, I could then do bold all waveforms. The default is when you click on a waveform, it bolds it, but if you do bold all waveforms, you don't have to click it. Kind of gets a little brighter. And you can change the background on these if you wanted. You can swap the foreground and the background. Now, this is one of my example I like because it's allowing you to reuse circuitry in the way that they do that. They're using, see, with this little phono jack coming in, they've set it up as a AC sinusoidal waveform input, and so they're using that to drive the circuit. Now, the way that they have this set, this is all using the same lower level schematic document. So on this sheet symbol, if we edit that and look at the parameters, they're defining, this one has C1 value and C2 value is set at these values over here. The only limitation on this, you can't use the repeat function. So you have to put each one of these separate, and they've assigned values up at the top. And then these values we're going to use down at the lower level. So here we've got the C1 value is 0.12, the C2 value is 4.7. I'll just control double click on that to pull down into here. And so here we've got like and I'll go down one more level. See, so down here there's just a simple little filter where you've got the capacitor and the resistors. And this is C2 value, R2 value, C1 value, and R1 value. Now, if I compile this, I should be able to see. Then if you click, see, here's all of the upper level references. If I click on here, I can change the intensity of those. But in the, I was doing it in 80/20. In the preferences, you can change it how you want. Let me just go and do that real fast. So if I go into my, I think it's at navigation. One of these is the dimming. That's for the highlighting method and schematic. And so there's an option here, and I found it before. I changed it in the 80/20 version, where if you don't want to see them, you can choose. You can set the how much it dims on those, which I can't find right now. But you can kind of see over here. See, it's this is 22, and if I click on each one of these, so this is like one microfarad. Sorry, it's so whited out. I forgot where the option to change that is. So if I click on each one of these, so you can, now it's using, so for each one of these upper level sheets, it's using a different value to drive those. And then so when you run the simulation, it'll then go through and it's going to do a parameter sweep on, and the way they have this set up is kind of neat. So see, the parameter sweep allows you, of course you could sweep it could also work in conjunction with like a DC sweep, where you can sweep a voltage source across a range of voltages. But with a parameter sweep, allows you to sweep a parameter across a sweep of values. So in this case, they are going to have a sweep value called sweep, and starting at 0 to 4 in steps of 1. And so you also have a secondary sweep, which will sweep the primary. Each value of the primary, it'll sweep the secondary a separate number of times. So you have to make sure you don't have too many sweeps, so you can get a large number of sweeps. Now there's right here in the simulation param analysis template, there's a global parameters, and this is where you set up your values. So they have, they've set, and this is my, now I had, because the initially, this wasn't working 80/20 because they have a if then else syntax. So what they do is they say if, let me get, I thought I saved that one back. It's over in my other, parametric auto equalizer. Just open up the example. Well, it's in the it has in the download example. It has an if then else. So it's saying if sweep is 0, then it'll then use this value, and so it comes in. And it's kind of neat that they. I was talking with the developer who's working on 80/20, and he was able to get that if then else working. And I'll just go ahead and run this here. Oops. Okay, this one. Yeah, let me open up my project, because that's the one I was modifying. And if I just go down to here, let's browse. I should have it just right in here. There's a parametric analysis. Sweep. And let me see if I have it in, it was in audio equalizers here. Because I had two different versions of this, the equalizer top. Let me just right click and explore. That's probably the best way. Yeah, so parametric hierarchy, I had the audio equalizer and PRJ. Yeah, so this is the one. Make sure for projects are here. Yeah, so parametric audio equalizer and audio equalizer. Okay, so now I'll just go in because the simulation profiles are associated with the project. So if I come in here now, I should be able to look at the setup. And let's take a look at the global parameters. Yeah, okay. So I thought I had saved my simulation, or the work group, but it didn't save that. So you can see here, so what it's checking, if it checks the sweep value, and if it says, it checks if it's 0, or if it's a 2, 4, 6, and it goes through and it varies all the values to cycle through the steps of the audio equalizer, and then when you run that, it'll show all of the different parameters from the results here. Just right click and fit document. Now in 8019, it takes about 2.5 minutes to run this, and it takes about, I think it's like 30 seconds in 8020. So it's not really exciting to watch, but you'll see it. See, it kind of runs through at each step value, and it'll show the different values over on the right. So it'll run through, and this is where if you don't, by default, you don't have the toolbar, the SimView standards. If I click on that, so if I wanted to stop it, so otherwise it would take about 2 more minutes. I can just click on stop. Now in the waveform viewer, they do have some cursor probes. You can do some measurements. So in order to use those, let me just close. I could delete this plot. You just right click on a waveform, and you can do. There's cursor A and B. Fortunately, you can't have different cursors per different plots. The cursor applies to all the plots in your waveform. So I have my cursor A and my cursor B, and you can move those along. If I grab the cursor's up here at the top, then you can move the cursor along, and it will. There in your sim data, there's a sim data panel. Let me just dock that over here, and it has your cursor information in the middle here. So it'll have some calculated values, like it has the B cursor minus A, and down here at the bottom we'll have some calculated values based on the locations. So if you're trying to figure out a frequency of a sinusoid, you just put the low point and the high point. I think I've got. Let me show an example of that one. Go to, like for here is a. See, let's go down here to the, that's a good one. Geometer. I think, well, if I go back to this guide we already ran before, this BCVF. So here we've got like a waveform that's here. Now first let me show you for the plots. If I go to the tools, document options, down here there's a number of plots per display. So sometimes the default is when you run a simulation, each active signal that you run will come with its own plot. So sometimes you get a whole bunch of plots, but it'll only show 4, and you get a scroll bar. So you can come over here and change the number of plots, from 0 to 4. If you choose all, it puts them into kind of a compressed view, so you can see multiple plots. But let me just go back. So that's under chart. Actually, that's tools, document options. So you have the number of charts that you can specify over here. If you just put one chart, then you get a bigger chart, and you get the scroll bar over here. You can scroll around. So here I've got the a waveform. I can right-click on here and choose cursor A and cursor B. Now, currently the cursor movements function is pretty limited. You have to turn. If I click on a cursor and then go to the wave, you'll see that there are some cursor movement commands. You can also get that in the SimView standard. So if you're going to move, but you have like the minimum point, as well as the next peak. So you have the next peak or next valley. So it gives you a little bit of control. I hope at some point that we'll have like more advanced controls. I'm kind of spoiled with PSpice, where they have their own language they built. You find this point, you go 3 steps to the left, and you turn to the right, and you can find some. But it helps you find specific points, and you can run a simulation, click the button, and you have that instantly. Here these are just really basic. So I hope at some point we'll have some more advanced. So for example, if I click on my cursor A, I can do like next peak, like next trough left, and see right now it's right over here, and I can grab this guy over here, and say I want it to come right up. I think if I want to get it right at the 0 point, it's a little more tricky, because we want to get these at 0. You can come in and change the point on here. So I think if I just type in 0, I went all the way to 0, 0. But sometimes you can manipulate those a little bit. You can use your arrow key, your left and right arrows. That's the wrong one. So if you get Yeah, because you want to get right at the 0 crossing there, and then over here it'll show me the frequency between A and B, so it'll show me the frequency between these two values. But of course you need to get these right onto the, you could drag around in here to kind of zoom in on the area so you can get a little bit better view on where those are at. And so you have like a B minus A, it shows the minimum, maximum, some average, so different values of those selected waveforms. So it gives you a little bit of a little bit of analysis. Especially, it's good for when you're running your if you want to calculate frequency or other values. Now there is under here you can run a fast Fourier transform on your display of waveforms. If you go under the chart with the FFT, but typically with the FFT you want to try to run your simulations with as many full periods as you can. The more periods typically gives you a better result with your Fourier, your FFT, and of course that'll show you the main Fourier frequency point. If you have any harmonics that are coming off of that, it'll reference those. And so that's based on the display data. There's also a fast Fourier transform you can enable from your transient analysis. So then in there you have to specify the base frequency, and so let me just pull back over here to what would be good. I have my op. Yeah, let's go to op. No, not that one. Like for the analog amplifier here, if I go over and so for transient analysis, so down here on the bottom, I have to uncheck the use transient default. So I've got Fourier transform. So you specify the base frequency and then the number of harmonics, so that can let you see a little bit. It works decently. If you take the online simulation class, it goes you through and a couple nice examples through setting that up. What's that for windowing as far as the FFT, or is it? Yeah, that I don't know. Probably. Yeah, but it will. So it just does calculates the main fundamental frequency, and then calculates the number of harmonics on either side. But so it's limited to what Spice does. There might be some more advanced calculations and some other tools. And one thing that is nice is that if you have everything set up in here, you can export out a netlist, and that can be usually load it into another Spice 3 simulation tool, or even I know LT Spice is really popular. Now, even though it's called XSpice, it's really Spice 3. We do have XSpice models that are in there, but it's primarily Spice 3 driven. So if you go design, there's this netlist for project, and at the very bottom, it's XSpice. You can also access that directly from the simulation. It's generate a mixed sim netlist is here, and you can do it from the toolbar. And so that'll generate now some of the options that you might have, the other simulator might not recognize them. I always say, as a rule of thumb, you should always have at least a second simulator so you can run your simulation and then compare the results between the two. So that's a good way to make sure that your simulator is behaving correctly and giving you the right results. And so for here, if I run now also you can on some of these probe templates, you can, if I go under the Simulate and Probe Manager, see they have a Bode plot as well as the magnitude of these, so you can get a analysis of those if I run the simulation. On there for the AC analysis here, so I can have, see this one has a phase, it has the dB output and the dB input. Now you can double click on these on the waveform, and you can manipulate these with an expression. So if I wanted to do, let's say, like input divided by output, or even, let me switch that, my output divided by the input. So then I've got my output. It gives you the output over the input. Now if you wanted to find your cutoff point over here, you can add in your cursors. So I have I right click on here, my cursor A and my cursor B. And then of course you have your high point over here, and then your cursor B. If you look in your sim data, you can have it shows you the B minus A over here. So if you're trying to find you have your high point over here, like the 3 dB cutoff point over this guy, you just push it down over so that you get so this is right around 3 here for the B minus A. So it gives you around the approximate frequency where you'd have your 3 dB cutoff. Let's see. I wanted my other. Now, so in here, there's a example which is called the dual polarity power supply. Now, this uses a transformer, and I placed a couple transformers from the miscellaneous devices just to look at how transformers work. Because if you're working with transformers, if we look at this transformer, if I look at the model, I'll double click on it and come down to simulation and edit. See, so this model, it's using pretty much all of these components, controlled sources and things. It's a full subcircuit, so somebody's put it together. But the typical transformer that you'll find is just going to use a special device, which is the coupling device. In that way, so in here, even though this is a transformer, if we look at the model, it's going to have two inductors, and it'll have this coupling device. So even though this is set a generic editor because they've added several different inductors and they've added these K devices down here. But this started out as the K device is the coupling device. So if we look at here, see they've got these K devices down here, and even in air you don't have 100%. The coupling value isn't full 1. That's why they put in 0.99. And so depending on the material, you're going to have a different coupling factor. So you've got, so here they have three inductors, and then they have the coupling between the inductors are set up using these K devices. So that's how they'll pretty much set up their transformers. Although you can get some more complicated transformers that use more of a subcircuit model, but pretty much they're just using that K device. And you can you can couple two inductors on your schematic by using a K device from I think that's going to be down under I don't think it's sources, but you can there's a coupled inductor. I think it's just if I go under the miscellaneous devices here, and there's a coupled inductor value in here. It's a CD. Okay, forgot which library it is, but there's a specific coupling, and you just place the couple value right on your schematic, and you specify the inductor 1 and inductor 2 and the coupling between them, so you can have inductor couplings versus using a built-in type transformer. Now, another thing I want to talk about is that you run into a lot is troubleshooting and troubleshooting convergence. So you've got this is a big issue that you'll run into is convergence, and there's a lot of common mistakes that you might make with your circuit. So I have this one. I took this from our training, and I had initially made this example for the training, so it walks you through and with mistakes that I've seen. Like this one is for capacitor bias. Although you really don't see a scenario like this where you have two capacitors in series like that, but if your circuit happened to run into something like that because capacitors are opened up with the initial bias, is it opens up all capacitors, shorts all inductors, and it calculates that initial operating point. And if it can't find a point, it'll fail. Or the same thing when you're running any analysis type, any incremental step, if it can't calculate with the specified tolerances, it'll fail. And I'll show you how to set the tolerances and check those up in a second. So in this case, this one would fail because of those are two in series. But more commonly is this one here. because it looks like the circuit looks fine, but inside an op amp, typically the way that they have it set up, there's going to be 2 diodes that are on the rail voltages. So they use those diodes to drive the internal circuitry, and so it requires the correct biasing on there. And you might remember back in engineering school trying to be fancy and do something like this, where you flip one circuit around. But in this case, I did this on purpose, where I had my positive VCC is 12 volts, and negative is, I flipped it around, but I didn't flip the power port on that, so it's a double negative. So instead of minus 12 over here, I'm really going to get positive 12. And it's going to turn the diode on inside of there, and get a convergence error. So you got to watch out for your polarity. Probably most of the time, you probably seen more like this, where if I got rid of this ground symbol, then just drag that over and up. So a lot of times, it's common practice for, you'll see a lot of schematics of something like that. And you just got to be careful on that, because this will, depending on the orientation of the source. And also the way when you think about Kirchhoff's voltage laws and current laws, SPICE handles, when you're doing measurements, it handles it a little bit differently, because it's looking at basically the current into pin 1 versus current out of pin 1. So when you're doing a current measurement, and you see the current you're expecting the current flow in one direction, but it's negative, it could really just be the direction of current if it's flowing in or out of that device. And sometimes just flipping the device around, if you're measuring current through it, will then give you the right. So it's mainly when you're doing current measurements, SPICE can fool you sometimes. And this last one with this shorted inductor, since remember now all of these sources in Altium Designer, they're ideals. That means there's no internal resistance that can be used. So when you just hook this source right up to an inductor, of course with the inductor, when you first turn it on, it shorts it out to calculate the initial bias point. So this will just short that right out, and you'll get sometimes when you look at the messages that are reported, like this says, if it mentions anything about like pound branch, for some reason we use pound branch as the current through a source. So you might get a pound branch through so right now this is saying, actually it said so this is saying, see, a voltage source VN and inductor has a inductor loop or a short. So some of the error reporting has gotten better. It used to just say, we got a pound branch and current, through this. So this is giving a little bit of a hint that it's through the inductor and the source. So then, one way to resolve that would be maybe put a series resistor in here, or if you take the SPICE class, it shows you how to build kind of an inline resistor where you can just netlist it in. And where you can then take, so you just manipulate the template and you put in a resistor, manipulate the pins. You can create extra nodes and create different, like virtual devices within that. Now within the simulation profile down the advanced options, you have all of your tolerances. So then when you have these checkboxes over here, that's where they're going to use the default value. And anything ending in a tol will affect your tolerances. I kind of wish they would group the tols together, but you can see you have your charge tol, abs tol is for current, and see the abs tol is pretty small for, it's down in the pico range. So, and that's the absolute tolerance of your current ranges. So typically you don't need to have your currents in pico range, especially depending on the type of circuit that you're simulating. So usually bumping that into maybe nano range, and maybe even micro, depending on how large of currents you're dealing with. So you have abs tol, there's VN tol. VN tol is not so bad, but the main tolerance variation is the rel tol. So sometimes, and usually you'll be playing with Reltol, because Reltol you can sometimes make it a little, 1 milli is not too big. Sometimes, usually I like to make that a little bit smaller by order of 10, maybe make it 0.1 milli. But this can be a big influencer whether your circuit converges or not. Now you've got your integration method. Now trapezoidal is the most simplest. This goes through, but it's faster. But it might not give as detailed calculations. We have the full gear analysis that's here, so you can switch your gear analysis type down at the bottom there. All right, so then, and now for the 80/20 coming up with the because currently for our digital components we use a custom, what we call digital SIM code, which is kind of derivative of the old XSpice. So it's more of a proprietary digital language, similar to what PSpice did with their digital. So in order to but XSpice also has its own digital type of modeling. So I'm not sure with 80/20 how they're going to handle the digital part. So so this is just a digital AND gate. And when you download the older legacy libraries, there's a lot of digital SIM code models. All of our digital components are done in SIM code. So all of your ANDs and ORs and all of the digital gates. And so this one here is, I'm not sure if this is just an XSpice one. I haven't even tried it in 8019. So I'll see if it. Yeah, see, so actually it's saying unknown is here. As I had been doing that in 80/20. So this is kind of a gray area between the different versions in the new simulator, because the new simulator it uses ngSpice, and so the initial plan was completely drop SIM code. So I don't know if you're using digital gates in there, or I guess that's not. Let's see, okay. So for the output. And so you can have, so there's digital models, so there's a lot of different sources that you'll find in the older one. Now, I wanted to mention Monte Carlo real quickly, because now Monte Carlo is a way that you can look at how variations in your circuit will affect your device. And it's really easy to set up Monte Carlo, because by default, all devices, you don't have to do anything to the models or anything. Everything has built-in tolerances. So you just come in, turn it on. See, they're set up pretty high at 10%, so you might need to modify those. So, but by default, all of these, there's nothing special you need to do. You just enable it. If you needed a special tolerance on a device, you'd have to come down here and click on it, and you come down in and set up you choose up your designator, and you can set up a custom device to have a different tolerance. But otherwise, everything will just be under the same blanket tolerance. You have the number of runs, and you have the distribution. It's either uniform, Gaussian, or worst case. So of course, there's uniform. It's kind of uniform over the entire range of values. Gaussian is kind of the bell-shaped curve, where you've got the plus or minus 3 dB variation. So you have most of it at the, it's going to be at the top of the curve. And then now worst case, it just randomly will take each device and either use the worst case, like plus 10% or minus 10%. So it just kind of randomly puts those in there. So it's not the worst case value that you can get that doesn't do any analysis of the circuit. It just locks them all through either the worst plus or minus 10. So I'll leave that at 10, and then we'll just go ahead and run. What's this one? For the output. And I didn't check it on. So let me just go back there real quick. So if I come back over here, and now the Monte Carlo needs to be run in conjunction with another analysis. So I see I have my transient Monte Carlo, just check it on right there. It's going to run for 5 times. If you run it for too many times, it'll take a significant, could take a significant amount of time, because it'll run at every incremental value. It'll rerun the values. Let me just go and add a probe here. It should be active probes. There we go. And, oh, that's okay. Oh, that's back in 20 again. So let me go back to 19. Look over here. Got my Monte Carlo, and okay. All right. So this is just looking at the output. So for each, and the way that it displays the output is for each run. For each run, let's see, invalid. For each run, it would go and put the Monte Carlo value. It'll tack it on the end, and you can export those out as to a spreadsheet or another math tool that you might use for making your calculations. Let's just go. There's a couple of these. Got too many open. Was that one? But I know we're kind of running out of time. I wanted to show that. I've opened it up for questions. I know it's kind of... Yes?
You mentioned earlier about your legacy library index yourself.
Mm-hmm. Mm-hmm.
Did you have
Yeah. If you email me, it's just my first last name, Derek, DEREK, .Jackson, JACKSON, @altium.com. And I have it's an Excel binary index because it's smaller, because otherwise the file's pretty big. So in that way you can download those and you can use them in your own simulation. But it's unclear what's going to happen with the next. Hopefully it'll make it easier. But right now that gives you a huge amount of components to experiment and simulate with.
Thank you.
Mm-hmm. Yes.
Is there any plans to support importing or exporting LT Spice?
I know they've been trying to work with LT Spice, or maybe even work with them, but I think now when you look at the basic LT Spice schematic, it's just a real simple ASCII. I've looked at it too, but so I think that it would be simple. I think now that we're kind of gearing towards more Spice space, that it's going to be more. It's more of a possibility. Maybe down the road, if something happens, maybe we can partner with LT Spice. But right now, so just as far as like importing schematic, or is it?
Either way.
Yeah, but you can export out a netlist. You just clean it up, and then a couple, because sometimes it'll complain about some of the options, or say if you just. Yeah, and you just clean up the circuit, you save it out with the .cir, and you load it in LT Spice. You can run our generated netlist right out of it.
You have existing models in LT Spice. Is there any way to import the netlist into Altium created schematic?
Unfortunately, no. That would be. Yeah, I haven't. Yeah, you can, but you can create a more of a netlist, kind of, and drive it as more of a component. But it's. Yeah, but there's no way. I know. I've been looking for that. If you find it, let me know.
There's a lot of stuff. A lot of people.
Yeah. All right. All right. Thank you, guys. Appreciate it.